Good afternoon, colleagues. So we continue our discussion on electromagnetic neutrino properties, and we are covering the theory, the laboratory experiments, and also physical probes. And in the part we are starting now, I would like to speak about some effects that arise due to non-trivial neutrino electromagnetic properties. So if you remember, just 2 lectures ago, we discussed some introduction to this topic, some electromagnetic properties, the basis. Then on the next lecture, a week ago, we considered neutrino electromagnetic properties and focus on the laboratory experimental constraints on the most important neutrino characteristics, electromagnetic characteristics such as neutrino magnetic moments, neutrino electric dipole moments, neutrino charge radii, and also millicharges, electric millicharges of neutrinos. And today we shall start discussion on effects, the influence on external electromagnetic fields and also matter on neutrinos. And one of interesting issue is that in some cases the influence of background matter on neutrinos mimic the effect of neutrino interaction with the external electromagnetic fields, in particular magnetic fields. And this is one of surprising results of the general problem of electromagnetic interactions of neutrinos. So, and once again, I would like to flash your attention to our review paper that we published together with my colleague from Torino, Carlo Giunti, a couple of years ago in the Reviews of Modern Physics with the title Neutrino Electromagnetic Interactions, A Window to New Physics. And most of the facts that we are discussing in some detail in our lectures are at least flashed in this paper. And also I would like to recommend to those of you who are interested in the subject also to read or probably just to see the contents of the supplemental materials to this paper with a lot of important for production concrete calculations. Also, we shall refer to these calculations in our lecture today related to investigations of neutrino electromagnetic properties. And now I would like to summarize the most important effects or phenomena that arise due non-trivial neutrino electromagnetic properties. So that can be termed the neutrino electromagnetic interactions. First of all, if neutrino is a massive particle, and if you remember in this case, even in the easiest generalization of the Standard Model, neutrinos should inevitably have non-trivial electromagnetic properties. In particular, at least the magnetic moment of neutrino or effective magnetic moment of flavor neutrino should be non-zero. This is an effect that arises due to one loop effect in the easiest generalization of the Standard Model, which we should deal when we suppose that neutrino is a massive particle, and we have to incorporate to the Standard Model the right-handed neutrinos, and within the one loop effect, we immediately get that the neutrino gets the non-trivial magnetic moment. So in this case, if we consider a heavy neutrino, a massive neutrino, it can decay to a lighter state of neutrino. This diagram is shown here with emission of a photon, just as a decay of a heavy particle to a lighter particle with emission of the photon, and the coupling of this photon to neutrinos are due to, for instance, non-trivial magnetic moment. Yeah. So if we consider the same diagram in background environment, then the same diagram will also describe another phenomena of a particular different nature in respect to neutrino decay, and it can be called as the Neutrino Cherenkov radiation. This is a radiation known from electrodynamics. If you remember, the electron moving in matter emit light, and in a very similar way, a neutrino moving in a background matter or external electromagnetic fields can emit with the same mechanism as the electron emit Cherenkov light, also Cherenkov radiation. And there is another very important phenomena that is also described by the same diagram, initial final neutrino state and the emission of a photon. And this effect was for the first time proposed in our papers, and I will speak about this phenomena in detail. And we call it the spin light of neutrino, SL as we just introduced this term. This is a new mechanism of electromagnetic radiation of neutrinos, and this radiation, a neutrino can emit this spin light when neutrino is moving in dense external environment in matter. And again, if neutrino has non-trivial electromagnetic properties, in particular magnetic moment, then neutrino can emit light, and we call it the spin light of neutrino. So there is another very important effect that is described by the second diagram here. The photon can decay to neutrino-antineutrino pair in plasma, and I would like to, this is the plasma decay to neutrino-antineutrino pair. Again, the photon is coupled to neutrinos due to non-trivial magnetic moment, or if neutrino has dipole electric moment, well, it can emit this, can decay to neutrino-antineutrino pair in plasma, and this is a very important phenomena from the point of view of applications in astrophysics, because the studies incorporation of this effect provide the best astrophysical bound on neutrino electromagnetic properties, in particular neutrino magnetic moment. I would like to once again to recall that up to now, neither from terrestrial laboratory experiments nor from astrophysical and cosmology observations, there is no any indication in favor of non-trivial neutrino electromagnetic properties. So all the effects that we are studying and discussing and their application to particular phenomena that can be found, let's say, in astrophysics, set an upper bounds on neutrino electromagnetic properties such as magnetic moments, millicharges, charge radio, etc. So this is a kind remark, and I would like to ask you to not to forget this. And one of the goals of the studies of neutrino properties is to find confirmation, or just to get the real values for neutrino electromagnetic characteristics. But this is the question of future research, both theoretical and experimental. So there is another important manifestation of electromagnetic properties of neutrinos due to electromagnetic scattering of neutrinos given by this diagram. A neutrino is scattered on electrons or nuclei, for instance, due to exchange of the photons, and again the photon is coupled to neutrinos due to possible non-trivial neutrino electromagnetic properties. And then there is another also very important phenomena that is termed the neutrino spin precession and the corresponding oscillations in external electromagnetic fields. This diagram is shown here. This is a photon that mimic interaction of neutrinos with these photons that describe the external electromagnetic field, or as again was for the first time proposed and studied theoretically in our papers about 10 years ago, or 20 years ago probably now. These oscillations, and what is very important, in this process, neutrino change its spin state. So let's say the active left fanning neutrino coupled to external magnetic field turn to the right-handed neutrino. This is, and then vice versa. So this process result in a neutrino spin, or if in addition the type of neutrino, I mean the flavor is also changing, then spin flavor oscillations. Normally it was believed and it was considered that the spin or spin flavor oscillations can proceed only in the presence of transversal magnetic field in the rest frame of neutrino, but as it was proposed and studied theoretically in our papers, there is another possibility of neutrino appearance or generalization of the spin or spin flavor oscillations of neutrinos due to interaction with moving matter. And we shall discuss this effect also in detail, and these phenomena also have quite important astrophysical applications. So now I would like to recall once again the story about effective magnetic moment of neutrinos and diagonal and transition magnetic moments of neutrinos. For instance, let's consider the easiest generalization of the Standard Model that we should apply when we study the non-zero mass neutrinos. And here are typical diagrams that were for the first time considered by Paul and Wolfenstein in 1982. They considered the generalization of the Standard Model, accounting for the right-handed neutrinos that should be done if you suppose that the mass of neutrino is 0. Then these loop diagrams, the calculation of these loop diagrams, inevitably provide the effect of non-zero magnetic or even electric dipole moments. So if we consider the mass states of neutrinos, then the magnetic moment mu e j neutrino, just this calculation of this diagram is shown in this frame. We discussed this formula. Gf is the Fermi coupling constant. Mi is the mass of neutrino, and here is the sum where f is a function that depends on the ratio of the charged lepton to W boson squared, and U is the mixing matrix, the neutrino mixing matrix. So this is the explicit result calculation of this diagram shown here. And if we consider I equal to J, that will be just a normal diagonal in the mass, neutrino mass basis magnetic moments. And if we consider I not equal to J, then we get that there is a transition or non-diagonal in the mass space basis magnetic moments. And due to well-known Glacial-Heliopolis-Majani cancellation condition, we can see from this explicit formula that due to the fact that the mixing matrix is unitary, so it means that the first term in the expansion of this f over the small value, that is the ratio of the charged lepton to W boson mass squared, cancel out due to unitarity of mixing matrix, and only the second term here will contribute, that is have a very small suppression factor, that is square ratio of these masses. So, however, the transition moments are strongly suppressed in respect to the diagonal moments, and as a result, if we consider one of the important effects, like I just also discussed a moment before, this is decay, when there is initial state of neutrino is not identical to the final state, so it means that this coupling with the photon is due to non-diagonal or transition magnetic moment. It means that really it can be expected that this decay is quite a rare phenomena. This is what I have already discussed, and now let's consider particular process, neutrino radiative decay. So the initial neutrino state decaying to a lighter state of neutrino with emission of a photon. This is a diagram. This process was calculated for the first time in 1977 by Sergei Petkov, and the effective interaction Lagrangian is shown here. Just in this next formula in blue, this is the effective contribution to the vertex function, and just I should say quite regular, simple calculation gives the rate of this process that depends on the effective magnetic moment of neutrino squared, that is the squared magnetic moment has possible two contributions from the squared magnetic moments and plus the squared dipole electric moments. If we consider some general theory beyond the standard model, where it is possible for neutrinos to have non-trivial dipole electric moment. And if we put numbers just to understand the scale and of these phenomena, it is possible to calculate the inverse rate that gives the lifetime of initial neutrino in respect to this process with emission of a photon. And if you just put some numbers here, and if we suppose that the mass of the massive state of neutrino is measured in some EVs, and if you just introduce also the value of the Bohr magneton, but you remember that the prediction of the easy generalization of the standard model provided the effective magnetic moment if many orders of magnitude less than the value of the Bohr magneton. So this is a number in seconds. So we shall have a very huge lifetime. So it means that really this process is very slow. However, this process can be applied to different situations that can be found in astrophysics, in particular in astrophysics, and this radiative decay can be constrained, and consequently we in such a way can have limits or bounds on the effective magnetic moments of neutrinos from different observations. For instance, by the way, not only in astrophysics, it is possible also to consider the reactor antineutrino fluxes and the solar fluxes. Also, the neutrinos from supernova 1987A also can be used to constrain the lifetime of neutrinos. And also, it is possible to include this effect and to constrain this effect due to observations of cosmic microwave background radiation. So, just to summarize, this process exists in nature, first of all, no doubt. Yeah, if the magnetic moment is not zero, then it is very slow process, and if you just incorporate this phenomena to real situations where the fluxes of neutrinos are produced that can be observed and measured in terrestrial experiments, then we can put some limits on the effective magnetic moments that determine the rate of this process. This is, I would like to say, the first very important effect that exists in nature due to neutrino electromagnetic properties and in particular neutrino magnetic moment. So there is another similar process, neutrino radiative two-photon decay. So it may happen that not one but two photons are emitted, and this is like it looks like. This initial neutrino is converted to a lighter final state neutrino with emission of two photons. So obviously this diagram is suppressed by the additional coupling of with the second photon, and alpha here is the fine structure constant that is much less than 1, as you know. So, but the benefit of this process, in a sense, that there is no Jim cancellation of this process, yeah, because this two-photon neutrino radiative decay is not suppressed, but there is an additional suppression due to smallness of the coupling, electromagnetic coupling. Yeah, so and of course this process also exists in nature, but if we just use the realistic estimations for the mass states, the masses of the mass states of neutrinos, we shall come to the conclusion that this is quite a rare process, and it's quite hard to expect that it will be observed or manifested somehow in experiments. So I have already mentioned that there is another set of processes with a quite different nature, but that are described with the same diagram. But the initial neutrino is converted to a final neutrino with emission of a photon, and now we just would like to discuss the Cherenkov radiation. So this is a radiation of a particle, of neutrino in our case, in presence of external matter. So this matter is characterized by the refraction index that is bigger than 1. Then this process becomes open, and initial neutrino is converted to a final with emission of the photon, and the Cherenkov rate is given by this expression. This is the matrix, the amplitude of this process, and just straightforward calculation result in this quite not complicated expression that depends on the refractive index of matter and also on the energy, and it is possible to make quite a simple estimation using, for instance, applying this result to considerations of the solar neutrinos in the terrestrial experiments. And if once get for the evolution use the value of magnetic moment or effective magnetic moment of neutrino on the order of the present terrestrial constraints, let's say from the reactor antineutrino fluxes that are 3×10⁻11 Bohr magnetons, then for the huge detectors of the volume of 1 cubic kilometer, water detectors, for instance, like the Baikal or other gigantic volume detectors, the estimation yields that it will be several photons in such a huge detector per day. So it means that, in fact, it is possible to think about how to measure this, but of course this is a very, very hard job. Yeah. So there are a vast variety of other radiative decays of the Cherenkov type that also can proceed, but in some cases there is even no need to go to theoretical models beyond the standard model. So, and I would like to point your attention on the Cherenkov radiation by a neutrino in a magnetic field. So, and I would like to stress that in this case, there is no need to go beyond the standard model. It means that we can consider here if there is a magnetic field, it induces additional effective coupling between neutrinos and photons, and also modify the dispersion relation for a photon. And in such a way, also neutrino can emit photons, but there is no need for the theory beyond the standard model. Moreover, if following to the studies, by the way, this for the first time it was discussed in the papers published by our colleagues from Department of Theoretical Physics, Galtsov and Nikitina, in 1972. And then it was also investigated in some details by Raffelt and Anisyan in 1997. So there is another possibility that in a medium, neutrino can acquire an induced Mealy charge due to interaction with the medium. And as a consequence, neutrino can, being a quasi-charged particle due to induced, not inherent, but induced by interaction with the external environment charge, a neutrino can act like an electron moving in a media, like being a electrically charged particle. So, and I would like to stress once again that there is no need to go to models beyond the standard model. So this option exists, this process, the Cherenkov radiation due to induced by interaction of neutrinos with external environment melee charge can proceed even in the case when the mass of neutrino is zero. So it means that neutrino can be described quite well within the standard model in its initial formulation when neutrino was supposed massless particle. So another Cherenkov mechanism, I would say, can appear when, in addition to external media, also electromagnetic fields are present, and there is a superposition and of effect of electromagnetic fields on neutrinos and the effect of neutrino interaction with the background matter. Also, opening the possibility for neutrino in initial state transition to the final state with emission of the photon. So now I would like to come to quite a new mechanism of electromagnetic radiation that is also possible when neutrino has non-trivial electromagnetic properties, and in particular magnetic moment that allows neutrino to be coupled to photons. That was proposed for the first time in our papers published together with Andrei Lobanov about 20 years ago. And we call this new mechanism of electromagnetic radiation of neutrinos the spin light of neutrino in matter. So here is the visual object, the visual interpretation of this phenomena. So neutrino moving in external media emits light. And at first, we developed the quasi-classical theory of these phenomena. We investigate, we calculate the rates, the power, the energy spectrum of emitted photons, etc., using the quasi-classical approach to description of the neutrino spin evolution in an external environment, including the possibility of presence of external electromagnetic fields and external background matter. And then later, in a series of our papers, also mentioned here in this transparency, we develop with our colleagues the quantum description of this phenomena. Of course, this is more complete because this is a quantum phenomena by its nature. And also we reproduce the quasi-classical results for the spin light of neutrino characteristics. So this is a quasi-classical theory for the spin light of neutrino. And also we consider the possibility of this spin light not only in the presence of background matter, but also we consider other type of backgrounds, and in particular we also calculated the spin light of neutrino in external gravitational fields. So why we term this new mechanism of electromagnetic radiation of neutrinos when this particle is moving in matter, the spin light of neutrino? Because there is a classic analogy with the classical theory, classical electrodynamics, where an object with zero charge but non-zero magnetic moment can emit light. And this is the magnetic dipole radiation, and the power is proportional to the second derivative of magnetic moment of the system squared. So, and we just termed this new radiation the spin light. This is a reference to our paper with Lobanov, published in Phys. Letters B in 2003, where we introduce this mechanism and describe it using the quasi-classical theory of neutrino spin evolution. I would like to mention in the very beginning that in this process neutrino change its spin states from the active left-handed neutrino is converted to the sterile right-handed neutrino with emission of light. So, and our quasi-classical theory is based on the solution of the quasi-classical neutrino equation for neutrino spin evolution. However, we further developed the quantum theory of the spin light of neutrino, and I would like to show here one of those latest papers dedicated to the spin light of neutrino and published in the Journal of Cosmology and Astroparticle Physics in 2017, where we examined different possibilities for the spin light of neutrino manifestation in different astrophysical environments. We examined the most typical situations and have found the cases where it is possible to expect that once this radiation would be observed in terrestrial experiments. And just before going in some detail in discussion of the spin light of neutrino, I would like to recall the main steps in the studies of neutrino oscillations, because the starting point of or the appearance of our understanding, of our knowledge that these phenomena exist in nature was connected with the discussion on neutrino spin oscillations just in a magnetic field. So I have shown this transparency in one of our previous lectures that recall the history, the main steps in the studies of neutrino mixing and oscillation phenomena. Or I will just repeat shortly. The whole story started now 67 years ago with the discovery, observation, or prediction of Pontecorva that in vacuum, if neutrino is a massive particle, there is a relation between neutrino and another type or antineutrino. At that time, in 1957, only one type of neutrino was expected to exist. I would like to recall that the second type of neutrino, muon neutrino, was discovered in 1962. And Pontecorva just said that if the mass of neutrino is not zero, then a neutrino is a mixed state of two different neutrinos. In other words, neutrino and antineutrino, and there is a mixing, and also he predicted the phenomena of oscillations. So just after discovery of the second type of neutrino, Japanese colleagues, a group of Sakata, just generalized this prediction of Pontecorva and also incorporate the transition or oscillations, mixing between different types of neutrino, different flavor neutrinos. Then Wolfenstein in 1978 calculated the effect of neutrino scattering of background matter on neutrino oscillation phenomena, and just about 10 years later, in 1985, Mikheyev and Smirnov, using the results of Wolfenstein, discovered that there is a possibility for the resonance amplification of neutrino flavor oscillations due to effect of neutrino interaction, neutrino scattering on the background matter. That is the famous Mikheyev-Smirnov-Wolfenstein effect. And what is now important for us, and that is the starting point of understanding, our just prediction for the spin light of neutrino, that very similar to the mixing and oscillations between different flavor neutrinos, if neutrino is a massive particle and if the magnetic moment is not zero, then neutrino can interact with the transversal in respect to neutrino propagation magnetic field, and there is mixing and oscillations between neutrino with different spin orientations, between left and right-handed neutrinos, and Cisneros in 1971 was the first who just predicted that there is a mixing and oscillations in the presence of a transversal magnetic field, for the case of mass not zero neutrinos, between left and right neutrinos. Then Voloshin, Vysotsky, and Okun just considered these phenomena, trying to solve the solar neutrino problem. And in 1988, in two papers, separate papers, Akhmedov and Lim and Marciana, they reproduce, or just they have proposed that very similar to Mikheyev-Smirnov-Wolfenstein resonance effect, there is also resonance amplification of neutrino spin and spin flavor oscillations in case neutrino propagate through matter due to neutrino scattering on particles of matter. So, and these phenomena exist in nature, and we have derived in a very short way the probability of neutrino spin and spin flavor oscillations in the transversal magnetic field. And here I would like to show the final expression for the probability of oscillations between left and right neutrinos, that is given by these two signs squared. And the second depends on the x. It is a distance traveled by neutrino from the source to the detector, to observer. And the first sign squared is the amplitude of oscillations. And when omega, this is explicit expression for the omega, depending on the particle number density, on the density of the environmental matter on which neutrinos are scattered, depending on this, if omega is zero, the amplitude, the first term here, gets its maximal value equal to 1, so it means the resonance. Well, and there is a correspondence we have discussed between flavor and spin oscillations, this phenomena, just only one remark about possible visualization of application in astrophysics. I have already mentioned this in this process, active left-handed neutrino is converted to the sterile right-handed neutrino, and if you just observe neutrinos from the sun, you will get a visible result, so it can be constrained. Also, these phenomena, spin and spin flavor oscillations in a magnetic field, are important for astrophysical applications, for supernova phenomena, etc. Why I am speaking now about mixing and oscillations, spin oscillations, because just discussing this particular matter on one of the conferences, I was asked, well, look, if there is a process where neutrino, there is evolution of neutrino magnetic moment, and if, again, recall the analogy with the classical interpretation of these phenomena, that was a stimulus for us to invent this name, spin light of neutrino. And the question was addressed to me, and whether a photon is emitted during the process of neutrino spin or spin flavor oscillations. Well, of course, in such derivation, there is no room for emission of the photon, but in principle, the photons should be emitted somehow. And my reply to this question was quite not certain, I should say. I just said? Well, of course, probably it is a fact that the photon should be emitted, but the process of this emission is very, very rare and not very important. But then, after that, we together with Andrei Lobanov just start thinking about this, and really come to the conclusion that indeed, when neutrino is propagating in external environment, the photon should be emitted, as well as when neutrino is propagating in external electromagnetic fields, or in particular in magnetic field. So that's why I discussed neutrino spin and spin flavor oscillations before starting our part related to some details on neutrino spin light. But before just doing this, I would like to once again to turn to neutrino spin and flavor oscillations, not in a constant transversal in respect to neutrino propagation magnetic field, but in the case of arbitrary magnetic fields with arbitrary orientation. Following to our papers, so we consider neutrino mass states with two helicities and propagating in a constant magnetic field with a transversal and longitudinal in respect to neutrino propagation fields. So we start with two mass states of neutrinos, both in two helicity states. So, and here is the effective Hamiltonian that governs the neutrino mixing and oscillations, and just the evolution equation for two mass states neutrinos with two different helicities is shown here. This is just a consequence of the Hamiltonian that is shown above. So, and what we can see from, well, for, of course, one can consider three neutrino flavor states then, and three mass states of neutrinos, yeah, but for simplicity, we confine ourselves to the case of two mass states and two possible further flavor states with two different helicities. So here are neutrino 1 and 2 with two different helicities, and neutrino mass 2 with two different helicities. And this is the terms of the effective Hamiltonian. What we can see. So the first conclusion that is obvious fact that the mixing between two different helicity states are due to interaction of neutrinos with a transversal magnetic field. So if we consider the first two terms here in the equation, so we should use the first two lines and two columns just to extract the effective Hamiltonian, and we see that the mixing between the first and the second type of neutrinos are due to magnetic moment of neutrino, mass state neutrino, coupled to transversal magnetic field. So this is a very reasonable and well-known result. Then, important addition that the coupling with the longitudinal magnetic field shift the neutrino energy. Indeed, the first line, the first column, stands for the effective energy of neutrino. This is a vacuum energy, and this is an additional term that appears when neutrino interact with the magnetic field, in particular on the transverse longitudinal part contribute. Also, it is suppressed by the gamma factor of neutrino, but nevertheless, there is addition to the effective energy of neutrino due to neutrino interaction through non-trivial magnetic moment with the longitudinal magnetic field. And what is very interesting is the third statement, the mixing between different mass states. So we have to consider different mass states. So the first state here and the second state here, yeah, is due to transition magnetic moment that interacts with the longitudinal magnetic field. So in addition to the mixing between two different helicity states of the same mass due to interaction with the transversal magnetic field, there could be a mixing between different neutrino states, mass states, that appears due to interaction of transition magnetic moments with the longitudinal, not transversal, but longitudinal magnetic field. So this is quite a new result, and in fact all these details should be counted when people trying to investigate the neutrino fluxes from the astrophysical objects with the strong magnetic fields, or if one accounts for astrophysical neutrino propagation in probably much less strong magnetic fields, but spread in huge distances of astrophysical environments. So then if we just incorporate and to go further, and if we just make a transition to the flavor basis using this connection between the mass states of neutrinos via the mixing matrix with the flavor states, then in the flavor basis we get this particular effective interaction Hamiltonian for the flavor neutrino states, also accounting for interaction with the longitudinal and transversal magnetic field components. And here there are effective magnetic moments for electron neutrinos, for I would like to recall that we confine ourselves to the two mass states and two flavor states neutrinos. This is magnetic moment of effective magnetic moment of muon neutrino, of the second flavor neutrino. And here is, for instance, the E mu. This is a transition magnetic moment in the flavor state of neutrinos. And these values are shown here. So all these effective magnetic moments in the flavor basis are calculated and are derived on the basis of introduced initial magnetic moments for the mass states of neutrinos, and also depends, these effective values depends on the mixing angle. Yeah, mixing angle. This is the set of effective magnetic moments, diagonal and off diagonal in the flavor basis, and here are the particular terms that accounts for the effect of neutrino interaction with the longitudinal component of a magnetic field. And what is important, if you look on these exact formulas, these terms are strongly suppressed by the inverse Lorentz factor for the mass states of neutrinos. Obviously, we should consider neutrino being a relativistic particle, so these terms are suppressed, but nevertheless they exist in nature. Yeah. And just for applying these general expressions for particular case of the transition between, let's say, oscillations between electron and muon neutrinos, we can write this effective evolution Hamiltonian, and here we just use the general expressions for the case of transitional oscillations between neutrino states of the same spin orientation. So this is really the flavor oscillations, and we have found that really the longitudinal component of magnetic field modifies the neutrino flavor oscillations. Yeah, the transition magnetic moment change the spin orientation and produce induce the spin or spin flavor oscillations, but the longitudinal magnetic field, interaction of neutrinos with the longitudinal magnetic field, modifies the initial flavor oscillations, yeah, without change of spin state. And the presence of the longitudinal, or account for the effect of longitudinal magnetic field, provide new resonances in neutrino flavor oscillations due to this particular expression. Yeah. So, and now I would like to turn to more general discussion of neutrino spin and spin flavor oscillations, mixing and oscillations in a magnetic field, and what is very important before starting the theory of neutrino spin line and matter, in matter. Also, we account for effect of possible motion of matter. This is a visual image of what we are going to discuss, and this is the reference to our initial first papers where this study can be found. So we consider neutrino left to right mixing and oscillations. This is a spin or spin flavor oscillations, depending on whether the type of neutrino, I mean the flavor, is changing or not changing. And also we consider neutrino flavor oscillations, so between electron and muon, due to presence of electromagnetic fields that are described by the tensor of F mu, depending on the type of external electromagnetic field. That can be a magnetic field, electric field, constant electric magnetic, or just we also consider the possibility of these mixing oscillations in the field of electromagnetic wave. Well, and we also account for interaction of neutrinos, scattering of neutrinos on particles of matter. And for simplicity, we suppose that matter is composed of electrons, neutrons, protons, maybe of muons, etc., on other particles. And we characterize each of the matter component by the density, invariant number density of these particles, and also we account for possible motion of matter as a whole, of electron component. This is the average speed of motion of electron component of matter. This is Vn, is the vector of motion, velocity or speed of neutrons, etc. And also we consider the possibility that each of the matter components are also characterized by polarization. So we consider in general neutrino behavior in the environment of electromagnetic fields and different matter composition, moving matter with different possible non-trivial, non-zero polarization of each of matter components. And this is a summary. This is a copy of one of our first transparencies indicating the result of these studies. This is a neutrino spin evolution. S is the spin vector. This is and we, in addition to the well-known from electrodynamics equation, this part is proportional to the magnetic moment, and this is the external magnetic field. We get that if matter is present and if neutrino is interacting with the background matter, then there will be an additional term very similar to the electromagnetic term, or that manifests the interaction of neutrino with the non-trivial magnetic moment with the external magnetic field. We get additional term that accounts for the interaction of neutrinos scattering on particles on the environment, or this weak interaction of neutrinos, and this J is similar to to the magnetic field, but quite different nature. These are weak interactions, and but the form is very similar to what we have in electrodynamics. And just that was the starting point, but then together with my colleague, Maxim Dvornikov, we provide a quite general inspection or investigation of neutrino spin evolution in presence of quite a general type of external fields. So we just start with quite a general Lagrangian accounts for different types of non-derivative interaction of neutrinos with external fields, such as the first term stands for the scalar interaction of neutrinos with scalars. Then this gamma 5 appears here. This is a pseudoscalar interaction of neutrinos. Then vector interactions, gamma mu, axial vector interaction, gamma mu, gamma 5. Then also account for tensor and pseudo-tensor interactions. So we just try to make quite a general investigation of the problem of neutrino spin evolution in presence on quite a wide type of general external fields, and have found a more general expression for neutrino relativistic, this is a quasi-classical theory of neutrino spin vector evolution, accounting for this these particular types of interaction, quite general, and we just get this expression. And from here it just follows that neither scalar nor pseudoscalar or vector interactions of neutrino contributes to the spin evolution, and only electromagnetic interactions and weak interactions can influence the contribute to neutrino spin evolution. This is quite a general conclusion that indeed is very important as a starting point for understanding what is the nature of, I just return back to the spin light of neutrino. And we are now ready to really to start the discussion on the quasi-classical theory of neutrino spin light that we first developed together with my colleague Andrei Lobanov, and then we further generalize these investigations of the spin light of neutrino using the quite complete quantum treatment of these phenomena. So, I think that probably we shall stop here, and next time we shall discuss in detail how just to move from this starting point to the final point, and to obtain the neutrino spin evolution equation for the general neutrino interactions, accounting for the effects of moving and matter, and also account to the effects of possible non-trivial polarization of particles of background matter. Well, thank you very much. Okay.